Hello everyone. Good day to all. Welcome to Saji's physics classes. Today, the 10th lesson of moving charges and magnetism. Chapter 4, grade 12. In the previous class, last class, we discussed force acting on a force between two current carrying conductors, force between two parallel current carrying conductors. In today's class, we will obtain the expression for the torque acting on a rectangular loop placed in a uniform magnetic field. Okay. Torque acting on a rectangular loop placed in a uniform magnetic field. Torque acting on a rectangular current loop placed in a uniform magnetic field. Okay. So consider a rectangular loop placed in a uniform magnetic field. See, I'm drawing a rectangular loop. This is a rectangular loop placed in a uniform magnetic field. Name the loop as A, B, C, D. Length of the loop is L, its breadth is B. So breadth of the loop is small b. Length of the loop is small l. Let L be the length and B be the breadth of the loop. Now it is placed in a uniform magnetic field. Let the magnetic field make an angle theta with the normal to the plane of this rectangular coil or loop. So this is the magnetic field direction, B, capital B. Okay. Let I rename the loop as PQRS because B we are using for magnetic field. So I rename the loop as PQRS. So B is the strength of the magnetic field. This magnetic field make an angle theta with the normal to the plane of the loop. See, normal to the plane of the loop is this one, represented by N, normal to the plane of the loop. This angle is theta. Okay. So let theta be the angle between normal to the plane of the loop and magnetic field. Magnetic field B. Okay. So this loop carries a current I. Suppose the current is I. Okay, through this loop, current I is flowing. So this current is entering through this end, leaving like this. Okay, so current is circulating. So through the arm PQ, current is upward, and through the arm RS, current is downward. See the direction of current. Okay, so PQ is a conductor of length L placed in a magnetic field. It will experience a force. That force is given by BIL sin theta. Theta there, that theta is angle between current and magnetic field, right? So this magnetic field, this current is in the positive J direction, upwards through the PQ. So force on it is what? Force on PQ is BIL sin theta. BIL sin theta. You know the equation. BIL sin theta. See, magnetic field is here. Per magnetic field and current are perpendicular. So sin 90 only. So you take BIL sin 90. Okay. Magnetic field and current are here perpendicular. This is the direction of magnetic field in the figure. Okay, BIL sin 90. This force will be directed into the plane of the paper. So what is the direction of this force? We can use left hand rule. Okay, left hand rule. Here magnetic field is in this way. Forefinger represents magnetic field. Current is upward. So thumb will point in the direction of the force. So the force will be perpendicular to PQ and inward. This is the direction of force. The force direction we can determine using Fleming's left hand rule. So magnetic field is along X direction. Current is Y direction. So magnetic field will be perpendicular to the PQ and inward, right? So that is a force. Force is what? BIL. Okay. Now you consider the side RS. RS current is downward. Okay. So what will happen? Direction of force will be opposite like this. Force on RS will be opposite. And these two forces are equal and opposite. So what they do? They constitute a torque. They will tend to rotate the loop. Total force will be zero, but they are acting on different line of action. So what will happen? They rotate. The torque will rotate. There is these two forces will rotate the loop. So there is a torque. Rotating effect is known as torque. So there will be a torque. Okay. If you find out the force on QC and PS, that will be like this. That will be opposite, but they cancel out. They will be along the same line of action. So force on the arm QR and PS will be along the same line of action, equal and opposite. They cancel out. Direction is given by left hand rule only. Okay. So only two forces act on the loop. Force on PQ and force on RS. These are equal and opposite. Okay, they do not cancel, but they constitute a torque. Now you can find out the torque. What is the equation for torque? Force into perpendicular distance between the forces. Okay. For that, I am just drawing that QR, side QR. Okay, this side is QR, QR of the loop. See the top side QR. And magnetic field was in this way, magnetic field. And normal to the plane of the coil will be this way. This angle was theta. Okay, so when you find out this angle, see the angle marked by that blue line. This will be 90 minus theta, right? And this angle, that will also be 90 minus theta, correct? 90 minus theta. Okay. And force is on the side PQ, the force is will be in this direction. F is VIL. From the diagram, force at the side RS will be in this direction. Okay, so two forces, you know. Now, what is the perpendicular distance between these two forces? Just I draw this dotted line. Okay, you complete the triangle. Okay, make this point as, say I am writing this point as M. See QN, QM. QM is the perpendicular distance between the forces. So how will you find out torque? Torque is equal to either force, magnitude of either force into perpendicular distance between the forces. So torque equals, what is either force? VIL into QM, perpendicular distance. Now you consider the triangle QMR. You can find out QM. And QR is the breadth of the rectangular loop. Okay, this QR will be the breadth. We imagined initially breadth B, length L. So from the triangle, you consider the triangle QMR, QMR. Consider the triangle QMR. See the triangle. So this angle is 90 degree. Just I marked 90 degree. And what will be this angle? This 90 minus theta. Did you see 90 minus theta? So this angle also will be 90 minus theta, this vertically opposite angle. So this angle also what? 90 minus theta. Okay. So this angle will be theta. When you consider this angle, the top angle, I will use a different color, red color, say. This angle will be theta. Okay. This angle was already, you know, 90 minus theta. So this is the triangle QMR. From QMR, you can find out sine theta. What is sine theta? QM divided by hypotenuse, QR. QM divided by hypotenuse is B, breadth. So we can write QM is B sine theta. Okay. So from the figure, we can find out that QM. I think you understand how you got the angle theta there. Okay. Normal and magnetic field theta, plane of the coil and magnetic field 90 minus theta. You can see a triangle there. So the top at the corner where at the angle R will be theta, because angle M will be 90 degree. Angle Q will be 90 minus theta. Okay. Therefore, angle R will be theta. Okay. So we can find out torque. Torque is equal to VIL. What is QMB sine theta? So what you are getting? VILB sine theta. So this is the equation for the torque acting on the rectangular loop. And what is this L into B? L into B is area of the loop. So we can write torque equals VIA sine theta. Here loop has one turn only. If you consider a loop of n turns, then torque will be multiplied by n also. For a loop of n turns, torque will be VIA sine theta into n. N VIA sine theta. So this is the equation for the torque. So what is that theta? It is the angle between magnetic field and the normal to the plane of the loop. Okay. So torque is NIBA sine theta. And you can see that torque is depending only area. It is not depending on the shape of the loop. So for circular loop also, you can use this equation. Any shape of the loop, this equation is valid. It depends only on the area, not the shape. Okay. So this is the equation for torque. Okay. Now, this theta is angle between magnetic field and normal. If angle between plane of the coil and the magnitude is alpha, then you can write, if the angle between magnetic field and the plane of the coil is alpha. Okay, then you can write theta plus alpha will be 90 degree. So theta will be what? 90 minus alpha. Then torque is NIAB sine 90 minus alpha means cos alpha. So this is the equation if the angle between plane of the coil and magnitude is given. So remember this equation also. And you know, torque is equal to NIAB sine theta. Okay. But I into A into N, this is known as magnetic moment. We denote by capital M. It is a vector quantity. So we can write torque equals NIAM MB sine theta. Okay. In vector notation, torque equals M cross B. So when a rectangular current carrying loop or a coil is placed in a magnetic field, what is the equation for torque on it? Tau is equal to NIBA sin theta, BINA sin theta, BINA sin theta. Okay, theta is the angle between magnetic field and the normal to the plane of the coil. If the angle between plane of the coil and magnetic field is given, torque will be NIAB cos alpha. Okay, and this torque will be perpendicular to M and B. Okay, I think the concept is clear to you all. Watch it again and again. Make your subject strong and score 100% mark for the examination. So now I end the class. Thank you for watching. Share it. Okay. Goodbye. We will meet in the next class.